Hello everyone, welcome to topic 1.5, atomic structure and electron configuration. The essential knowledge for these set of notes will include the atom is composed of negatively charged electrons and a positively charged nucleus that is made of protons and neutrons. Coulomb's law is used to calculate the force between two charged particles. In atoms and ions, the electron can be thought of as being in shells or energy levels and subshells or sublevels as described by the electron configuration. Inner electrons are called core electrons and outer electrons are called valence electrons. The electron configuration is explained by quantum mechanics as delineated from the off-bow principle and exemplified in the periodic table of elements. The relative energy required to remove an electron from different subshells of an atom or an ion, or from the same subshell in different atoms or ions, ionization energy, can be estimated through qualitative application of Coulomb's law, meaning no actual calculation. This energy is related to the distance from the nucleus and the effective or shield charge of the nucleus. And so we have Coulomb's law equation that we are going to deal with here. Please note that there are no calculations directly related to those. It is just specifically qualitative. Like, you know what the equation is and you know how to qualitatively use it to make an argument for the energy of an electron and how the question or specific problem asks you to deal with it. So, looking at our notes, atoms are made up from protons, which are positive neutral neutrons and negative electrons. The nucleus contains the protons and neutrons, while electrons move around the nucleus in an electron cloud. The majority of the mass of an atom comes from the protons and neutrons, while most of the volume of an atom comes from the electrons flying around in the electron cloud. Electron configurations are a way of describing the arrangement of electrons within the atom and are predicted by the quantum mechanical model of the atom. By solving the Schrödinger equation, we obtain 4 quantum numbers that describe the probable location of the electron around the nucleus of an atom. If you ever have heard the Schrödinger's cat and whether or not when you put it in a box it's dead or alive, you know probably where it's at and whatnot, but you can't know specifics and for sure's about the cat. And that's tied into the electron. You can give a very probable area, but the smaller you make that area, so the more you zoom in on that electron, the less likely you are to be certain that it's actually there, because you're reducing your area that it could probably be within. The quantum numbers describe that space that it is most likely to be in with a 90-something% chance. Right, but you make that space smaller, you reduce those quantum numbers or get rid of them or parts of them, and your probability of finding the electron in that region decreases. Okay, so the inner electrons are called core, and outer electrons are our valence. Okay, and then we have a description of all the different quantum numbers. You do want to understand the principal quantum number n, right, which is its energy level or ring, and that is how far it is from the nucleus, right? That is tied directly to the periodic table, because it's the periodic table based off of laws of periodicity is arranged so that everything lines up like that, and they then saw that the principal quantum number matches the energy level and that they are organized on the periodic table by those periods. So that one is one of the most important ones. The others are good to understand, but we're going to focus more on the qualitative application, so like the SPDF, right? But not necessarily, hey, what are the numbers? Okay. The assignment of quantum numbers in the AP, all 4 of these is not part of the AP exam. So this is here just for you to know that they exist, that the principal quantum number is the one that you really need to know, but being able to assign all 4, not necessary. Moving on. So electrons are occupied in orbitals. There are 4 different cloud shapes that describe the space that electrons are most likely to occupy. These are called orbitals. They are given letter designations. The S-shaped cloud is a sphere. The P-shaped cloud looks like 2 balloons tied together. I kind of think of them as like a two-prop propeller. So that P orbital is kind of a propeller shape. Okay, the P orbital can be arranged in 3 orientations around the nucleus. This picture shows the S orbital and the 3 different P orbitals apart and together. Since the orbitals are electron clouds, they do and can overlap. Each orbital can fit 2 electrons with different spins. So the picture shows the potential location for 8 different electrons. And the darker shaded areas are the ones with the highest probability of having an electron in there, or in that region. Okay, next up we have energy levels, right? So that principal quantum number. Different distances from the nucleus are called energy levels. Okay, so the S orbits here are shown cut in half so that you can see inside, and thus you see the dark areas, which is the energy level where electrons are located. So electrons are quantized. Remember, Bohr kind of defined that by looking at the spectrum of various elements and seeing what colors it emitted, and that it didn't emit the full spectrum, but it emitted very specific quantized color bands. So electrons have quantized energy. Each energy level has different shapes that are possible, and so when we have principal quantum level here, or your period number, you have different orbitals that can be present. And then electron configurations describe the model of the atom by showing shells, or energy levels, and subshells. Okay, and so we have a little graphic here to kind of show you that. Each dark line shows a subshell that can hold up to 2 electrons. Electrons occupy the subshells starting lowest energy levels first, and by lowest energy level we mean the ones that are closest to the nucleus. They would require the greatest energy to remove them. Remember that atoms have negatively charged electrons and a positively charged nucleus. Now this ties into Coulomb's law, with the Coulomb's law equation that you should be able to know what it means, but calculations aren't directly tested. So this tells us that the force between charged particles is proportional to the product of the force is inversely proportional to the squared radius between them. So it's directly related to the charge values. So bigger charge numbers, bigger force, and inversely proportional to the radius or the distance. Okay, so the force decreases further away, and higher charges and smaller distances result in greater forces of attraction, as long as those charges are opposite. If you take physics, it might be different, or it will be different, because they look at different types of charged bodies. This explains why it has more energy to remove, or takes more energy to remove electrons that are closer to the nucleus. They are closer to a charged body, and so they are thus held more tightly and require more energy to overcome that attractive force. In addition to the distance, the electrons that are on the valence shell, so valence shell electrons, experience less of the nuclear pull because the electrons that are in the core of the atom block or shield the attraction of the nucleus. from the valence electron. So it acts as like sunglasses. The core electrons kind of shade or shield the valence electrons from the full power of the pull of the nucleus. So we have some rules for electron configurations. The off-bow principle, which means to build up. That means you start low and work high. So you add to the lowest subshells first and you work your way higher. We have Hund's rule, which means you have to fill single before you double up. So you should have one electron before you double any up. I kind of see this as like you go on vacation, you guys are going to share like beds with your family unless there aren't enough beds for everybody to have their own, right? Everybody's going to have their own before they double up. Okay. And then we finally have Pauli exclusion principle, meaning no two electrons can have the same 4 sets of quantum numbers. What that means is that in one orbital, you can't have 2 that are up or 2 that are down, and we'll look at that. Those are not okay because they are technically occupying the same orbital with the exact same spin. And that means that they have all 4 quantum numbers. If they're in the same orbital, they all have 4 quantum. The first 3 are going to be the same. The last one should definitely be different, which means that one has to be up and one has to be down. And so that is the expectation there. So we can use the periodic table to help us with electron configuration. So we can represent it one of 2 ways, and depending on what you did in your previous class, you might have seen one or both of these. Okay, and for me, if you had me, it would have been very brief that we saw one of these. We will use the periodic table because you get the periodic table on exams. You do not get those charts on exams. Okay, so how do we write the electron configuration? Oop, I thought that was a highlighter. Still not a highlighter. There we go. Okay, the key idea is that electrons occupy the lowest energy levels first, right? And you want to be able to identify your S block, which is your groups 1 and 2, your P block, which starts with boron, goes all the way down and over to neon's the top, and then down in that block. And then you have your D block, which is your transition metals, and your F block, which are your lanthanides and actinides, and being able to use the periodic table for that. So this is going to be review, hopefully, and so you will need your periodic table to do that. So here we're looking at this, and we have the electron configuration for nitrogen as follows, where the letters are subshells. These are the number of electrons there, and the big numbers in front are your principal quantum numbers. So that's the energy level or the period, those big numbers in front. The letters talk about the shape of the orbitals, and this comes from what block it's located, or it doesn't come from that, but it's organized that way so it's easier for you to figure that out, and it helps with organizing based off of periodic trends and properties. And the smaller numbers on the top, the superscripts, tell you about the number of electrons in that type of orbital. So how to complete an orbital diagram. Orbital diagrams are very similar to electron configurations. However, they show the electrons as arrows and provide additional insight into the interactions between the electrons in the shared orbitals. We will start by filling orbital diagrams, but they are often simply horizontal. So usually it's just straight linear, and it's not like this, just because it's easier to write that on a piece of paper and not take up the whole page. They should be written as half arrows, but those are really hard to put into a computer. So they're shown here as full arrows. This represents that it is a half spin up or a half spin down. So make sure you're using half arrows when you're writing. Always start by filling the lowest ones first, and we're going to practice this. So this is here for you to reference as you're studying or working on problems as you're on your own. So we have some examples here, and I'm going to do them really quick. So we have just the setup. And so if we were to fill it for oxygen, we know oxygen, as we go through, we have in the 1s, we have hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, and then oxygen. Notice I filled single before I doubled up in the orbitals. I did up, then I filled down, and that's just by default, like half up first, then the half down, but it doesn't matter really which one you do first, but traditionally it's half up first. You can see the linear form of the orbital diagram below. So this is for nitrogen. There are 2 ways to arrange the electrons for nitrogen, but only one follows Hund's rule and minimizes electron repulsion. Here we double up before we fill up, and these 2 electrons, because they have opposite spins, even though they have opposite spins, they have the same charge, they're going to repel each other because they're in a very close spot, and they don't have enough energy to jump to a new orbital. So this is not appropriate. They're going to fill their own bed first, or their own subshell first, before they go and double up. Okay, noble gas or shortcut electron configurations. As you can imagine, electron configurations can become very long and tedious to write. There's a shorter way to show an electron configuration. However, you must be able to write both the electron configurations the long way and the short way. You have to be able to do both. You can't just like cop out and do the short one. To write an electron configuration using the short method, you start by locating the noble gas preceding your element. This is why it's called a noble gas shortcut, noble gas electron configuration, or the shortcut. The noble gases are elements in group 8A on the periodic table. They're your far right group. They are known for being unreactive. They are unreactive because they have filled valence shells. So it makes them a really good place to start with a shortcut. The fact that noble gases are unreactive is why they are chosen for the noble gas shorthand electron configurations. So this takes the noble gas before the element and then continues from there. So let's look at how we could do that. So we have the complete electron configuration for calcium as 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2. To do the noble gas electron configuration for calcium, we see calcium is here. We go to the noble gas behind it or before it, and that is argon. So we write argon first, and then we write 4s2 after that. They have an 18 here. You do not need to include that because you can tell from the periodic table that it has 18. You can include it. But what this is saying is that since argon has this electron configuration and it is an unreactive noble gas, we can use it to start our shortcut. Okay. So let's do some I do's and we do's. So write the ground state electron configuration for arsenic. So I'm going to pull this up so we can see it here. Arsenic. So what I was saying earlier is that this is S, this is D, this is P, and then the F block is usually shown below here. Remember that D fills the N-1 and F fills the N-2. And we'll do practice with it in class as well as on your assignment. Okay, so arsenic is AS, which I wrote over it. Oops. Arsenic is here in the P block. So we're going to start at hydrogen, and we're going to write directions to get to arsenic using the periodic table. So starting at hydrogen, which is not shown either, hydrogen and helium gives us 1s2. Then we go to lithium and beryllium, which are 2s2, continuing on into the 2p block, and we count boron, carbon, nitrogen, oxygen, fluorine, neon, that's 6. And we go to the next row and we continue 3s2 for the 2 there, Then we go to 3p6, third period, P block, 6 elements. We have not gotten to arsenic yet, so we continue to the next one. We have 4s block, there's potassium and calcium for 2. Then we hit the D block, which is n-1, so we have to do n-1, which is 3. N is our principal quantum number, so 3D, because we're in that block, and then we count, and we get to 10, all the way over. So that leaves us at zinc, so now we hit the 4P block, and we count until we get to arsenic, which is 3. Gallium, germanium, arsenic. So there is our ground state electron configuration for arsenic. If we were doing the noble gas shortcut, we would start at the previous one, which is argon, and continue from there. Argon has this electron configuration, so we would write 4s2, 3d10, 4p3. Okay, I want you to pause the video and write the electron configuration for calcium ion, which has lost 2 electrons. Do not forget to show that it has lost 2 electrons. Okay, pause the video and do that, please. Okay, so from this you should see that calcium lost 2 electrons. The 4s orbital, you start with the highest one, the one furthest or highest in furthest out, highest in energy here. So we lose 2, we subtract 2 here, and so that's the 2. So you can write it as this. I cross my zeros so I can tell them apart. Usually cross my zeros so I can tell them apart from oxygen. So we can either write the top one or the bottom. You should not write argon. That's not okay. Like argon by itself, no thank you. Okay? For the ion, the nearest noble gas would be the one above argon, which would be neon, and then you continue writing 3s2, 3p6. Okay, complete the you-dos for this set of notes, and you can check your work in class. Thank you.